Let's go straight into it. So we come from the point of view of optimizing a network. What if the optimization has to follow certain constraints? Like, say we want to constrain a transportation network, as Caterina was mentioning, but the optimal solution, for example, gives you conductivity values. So the μ's that Caterina was talking about before, which correspond to these thicker edges, are way above a certain threshold. So we cannot afford to have like such big connectivities on networks, meaning the roads cannot be that big. Like, say the unconstrained optimal solution that we find gives you like roads which have 7 lanes around the central node. We cannot have that. They're too expensive. So this scatter plot is like the size of the conductivity, and this is like all the edges from the graph. So we say, for example, this is the 25th percentile, so like 25% of the nodes are here, 50% of the nodes are here. Say we want to get like roads which are as big as 2/3 of the other nodes require. So if 2/3 of the nodes are fine with the conductivity below that threshold, we can impose that all the nodes, all the edges also follow below that threshold. So what we do is impose a capacity constraint, and we then get a network which is which satisfies and fulfills this constraint. Obviously, a lot of the edges are gonna saturate the capacity constraint, but basically this is to provide a motivation of why we do constrained optimization. Like, again, in transportation networks, it might be that the roads or the train lines get too busy for a realistic implementation of this optimization solution, and so we have to introduce constraints to apply real world cases to the mathematical background. Another example could be budget. For instance, if you have the cumulative sum of the capacity of the conductivities, so the thickness basically of the edges in the network, and for the unconstrained case, it reaches a certain value, but then say we're implementing a cycle network to be built in the city, to be rolled out in a new city, but we only have budget of like 100 million instead of 150 million, assuming each edge costs 1. Then we're going to have to impose a budget on the optimization process itself, and what this gives us is a new network, a new solution, which fulfills these constraints. Let's take a step back and look at the mathematical formulation of the problem. So this is going to be the optimization side, which we're then going to link up with the optimal transport side. From a purely optimization side, we have an objective function, needs to be minimized, and we have a feasible set called C, which is the set of all the possible values in the domain of the variables, which is in this case like a vector, where n could be, for example, the number of edges in your graph, but it has to satisfy certain constraints. For our cases, for our case studies, we're mostly going to be considering inequality constraints, so constraints that have to be bigger than 0, which make it for easier mathematical application. Some constraints could be positivity, for instance, capacity. So all the edges, for instance, in the graph have to have a positive conductivity, because it wouldn't make sense with negative conductivity. For instance, all the edges, as we saw, might have to be below a certain capacity bound, because we cannot build like roads bigger than, say, n lanes. We could have nonlinear constraints or budget constraints, as we saw before, which then become global constraints rather than on a specific, on individual edges. So this one can apply to each edge. So each edge has to be positive, each edge has to be lower than capacity, but then when you go to the budget, it becomes a more global constraint. Now, the key novelty, say, of the approach that I'm following in the project that I'm currently doing. So the project I'm currently doing, again, stems from Caterina's research of optimal transport on networks and optimization in general on discrete systems. And we add constraints, but the way we add the constraints is not at the position level, but rather on the velocity level. So if we take the connectivities as your decision variables before, so the μ's, we then apply constraints that would be naturally on the positions, so on these connectivities, and we move them to the velocities. So we take the time derivative of these connectivities, and we then impose constraints on that. And why this is important is because this approach allows you to move away from strictly convex feasible sets and allow you to deal with, again, non-convex feasible sets. So for instance, you can have something like this, that's a convex one. If you have something like this, that's non-convex. And if you have like no convexity in the visible set, by moving your constraints to the velocity level, you always end up with a linearization and convex approximation to the feasible set of the velocities. So this is feasible set at position level, but we're going to move to the feasible sets of velocities.
What do you say always? Oh, you can copy that.
No, basically, what do you mean always?
Because you said when you go from position to velocities, you always end up in a convex solution, right?
Yeah.
But why always?
Because we construct it in such a way, it will become clear in the next slide.
So your constraints allow you for this transportation.
It's not to do with the constraints itself, it's the way you build the approximation of the tangent cone. So the next step is like a visualization of what I've just said in the slide before. So this is the feasible set in the shape of an ellipse. So it's already convex. And obviously lying with your optimization procedure inside this feasible set gives you the solution. But this is a position-based approach. If we then move to the velocity of a certain point, like you say your iteration point is now x on the boundary, you define the velocity as you've seen just before. So if we're in continuous time, it's just the forward time derivative. If we're in discrete time, so in like algorithmic context, then it's just the difference between the two steps, but divided by the time delta. So this wedge, this green wedge, is the tangent cone. So it's basically the set of all the feasible velocities. Feasible velocities are defined as vectors, directions, velocities, which point from a given iteration point into the feasible set. So if a velocity was pointing here, it would be not infeasible, but this is a feasible velocity. And the set of all these feasible velocities is the tangent cone. So let's make it a bit more precise. Partial C is the boundary of the feasible set. C is the feasible set itself. If we're on a boundary, so if x star lies on delta C, the set of feasible velocities is given in 2 dimensions simply by the velocities included in the 2 tangents. If you're inside the feasible set, every direction is feasible because you're always pointing inside the feasible set. If you're outside, the feasible set is an empty set. Sorry, the tangent cone is an empty set because there's no direction we could point you inside. Just to rephrase that again, the tangent cone is the set of velocities v belonging to the same set of to the same domain as the positions themselves, such that every velocity within a product of, say, the gradients of constraints. So these are constraints which define what the feasible set is. So if you only had Rn, all space would be feasible. Since you have constraints, you have to reduce the space. And based on the negative gradients of these constraints, anything which inner product with these gradients gives you a positive value, so it would be this with this would be negative, is a vector in the tangent cone. Now, this is only valid for velocities of points which lie at most on the boundary, but not outside of it. And this is where the approximation comes in. If we then allow for iteration points which go outside of the feasible set, then we define a new feasible set, a new sort of an extension of the tangent cone, which is the set of feasible velocities. So instead of being on the boundary, this x star lies outside, and we have a non-zero tangent cone-ish, which is this p alpha, which is the set of velocities which point more strictly towards the feasible set. So it brings you back. So imagine you have an iteration procedure where your axes go like this, and at some point you go outside. In most in other gradient descent methods, you would be projected back onto the feasible set if you end up outside in an iteration step. In this case, we don't do this projection on the position at the position level, but we move this projection to the velocity level. So at this point here, you can say, okay, x is outside of the feasible set, but the set of feasible velocities, which correspond to like where am I going with this iteration, where am I going with this trajectory, has to be pointing towards the feasible set again. And this is done by, again, imposing a similar condition to the one that we have for the tangent cone, but it's stricter because this does not only need to be greater than 0, it needs to be greater than this negative value, because it's actually positive because G are the constraints. The set IXR is the set of constraints which are being violated. So obviously, if you're outside the feasible set, some constraint is violated. You cannot be outside the feasible set and satisfy all the constraints, because the feasible set is defined as the region of space where all the constraints are met. So you're outside. Since we're dealing with G greater than 0, for most of our constraints, a constraint violation has to be negative. So G is negative. Alpha is a slackness parameter, it's a constant. It just tells you how much, how strictly and how fast you're going to have to be brought back into the feasible set. And it's always positive. So this is negative. Sorry, the whole thing is positive. So it's a stricter bound than the tangent cone itself. So it's basically saying, instead of doing this projection of the new X star point, which ended up outside, we're going to be doing a closer, closer wedge extension of the tangent cone. And here the velocities will not be pointing necessarily back in. The way these, the reason why this is helpful is because you don't have to project at the position level every time you end up outside of the tangent, outside of the feasible set, but you can do this projection at the velocity level, which makes for a smoother trajectory of axis rather than fa, 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 and so on and so forth. The reason why we decide what the condition on the feasible set is, the feasible velocity set is defined like so, because if you integrate it for time, it gives you an exponential decay. Well, you don't even need to integrate it, but you can already see, because this nabla is taken with respect to the muse, or the axis in this case, which is the x dt in the velocity. So if you already rewrite it, it tells you that the constraint violation is going to decay exponentially, which is used in then the mathematical proofs for showing that this is a very valid formulation of the problem. I know this was a bit tricky, and I might not have explained it very well. So if you have questions, I'm happy to go through certain parts of this. If it wasn't
Why don't just do projected gradient descent?
Because this has a more I think a more physical interpretation, in the same sense as like Katerina was talking about the physics, but also because it's more numerically stable. I think that
you will show it in one of the next slides with the quadratic flow.
Yeah, exactly. I mean, the projection descent, projected gradient descent happens, but at the velocity level. Yes, as Katerina mentioned. Okay. So no, it's not here yet, but this is just to reformulate the problem. It's just as Katerina mentioned. L here is, so this is the definition of fluxes as pressure gradients. This is the Kirchhoff law, where P is the incidence matrix. And this is the dynamical equation, which again is reformulated in terms of the Lyapunov. So this is the connection between the dynamics and the optimal transport. And S is sort of a metric. So it's mu to the beta over L, I think with factor of 2. It's just a numerical factor. But the key point here is that we define the right-hand side of the dynamical equation as F, which will come in later. The optimization problem follows the same procedure as before. This is the equivalent of J in Joule's law that Katerina mentioned, but it's restated such that you don't have to impose Kirchhoff's law and constant cost law, the one that had the sum of mu's times the cost was a constant K. This has already been incorporated to reformulate Joule's law into this, and this leads to a fully unconstrained optimization problem. So we can use this to then compare any constraints that we add to. Because obviously, even though it was unconstrained, the constraints in Katerina's problem were like, you have to, all the total cost has to be a constant, the sum of all the connectivity has to be a constant. The Kirchhoff law has to be applied, which is that. But in this case, everything has already been reformulated in one specific cost, like cost function. And so we can treat this as the unconstrained benchmark against which we're going to be comparing for the various constraints. And this is where the projection comes in. So in order to go from the unconstrained dynamics to the constrained dynamics, so remember it was mu dot equals f, this line. In order to allow for iteration points, so now we've switched to mu's instead of x's. In order to allow for iteration points mu's which are outside the feasible set, we need to introduce a reaction force. The reaction force is a term which goes into the dynamical formulation of the problem, but this reaction force is always chosen so as to match the unconstrained dynamics as closely as possible. So basically what we do is the projection at the velocity level, where we say the velocity at this point is going to be such that the value of r is minimized. So v, so this is mu dot is the same as v, because this is a generic v chosen from the feasible velocity set. V is minus f is this r, and the value of v, mu dot, which minimizes this reaction force, is the one that we're going to be using for the update rule. So the update rule is always mu k plus 1, mu k plus t mu dot. Okay. So this mu dot, or t in continuous time, is what we need to find in order to update our algorithm. And the value that we find is chosen in sort of according to a geometric argument in a way to minimize r, this reaction force. So the projected descent comes in, but we move it to the velocity rather than to the position so here.
And maybe the answer to your question is now this is valid regardless the constraint. So this is always a quadratic problem. Which is a convex problem, very simple. You can either do it analytically or numerically. Whereas if you have the classic project, grading descent from the position, there are cases where you have no linear constraint, non-convex constraints can be very complicated.
But how do you guarantee you satisfy the initial constraints here? I see for this particular case, what you had before. Right?
It's okay, yeah. The way the constraints are satisfied is by seeing whether this condition is satisfied. So this condition moves the constraint from being again at the position. So of course, if say x is here, then maybe we have a mu which is greater than capacity, and then you have to plug you have to put a Lagrange multiplier to the constraint and put it in your quadratic problem. But instead, what you can do is you can use this definition, this condition on the velocity, and you're guaranteed that this constraint violation is going to decay exponentially to then define the reaction force which enters your quadratic problem. So this is how you're guaranteed to satisfy the constraints at convergence. You don't have to satisfy the constraints at every point, because this method, the whole point of this method is that you can go outside of the feasible set. So constraints do not have to be satisfied all the time, but the velocities will guide you along the trajectory in such a way that you always end up on the minimizer.
Even if C is non-convex?
Even if C is non-convex, because this will be a convex approximation of the tangent cone. So because exactly that's the power of it. So if you start with a non-convex feasible set, it doesn't matter, because what you end up doing is you end up doing the quadratic problem on the velocity, and the velocity has to lie in the feasible velocity set, which is this yellow shaded wedge, and this one is always convex because of this. So this one you can always prove that it will converge. And this is the algorithmic implementation, so we can go through it step by step, and this probably will make things easier. Did I do it step by step? No. Okay. So we start with the graph. So we go back to the problem setup as Katerina had. We have a graph, a network, so a graph with a process on it. And we want to optimize the process that runs on this graph. The process is usually framed in terms of these connectivities, which you can think of as the capacity of each edge. The capacity, or just how thick it is, how much traffic it allows on it. And of course, it was in the feedback mechanism equation with the flux. So it's the two things are very strongly coupled. You initialize your connectivities at time equals 0, and then you enter while this problem has not converged yet. First, we solve Kirchhoff law. So with μ's, we find F, we find the pressure values at the nodes using Kirchhoff law. Next, we find F, which is the right-hand side of the dynamical equation as we had before. So mu dot equals F. So we find this F. And with this F, we can then go and see how many of well, not with the F, but then the next step is you find which constraints are active, meaning which ones are violated. So you imagine this is not the t equals 0 anymore. Now you're just in the loop. It's a given t different from 0. And at this t, you need to check whether your mu lies outside of the feasible set or inside of the feasible set. Assume it does lie outside of the feasible set. So some constraints are violated. When constraints are violated, you have to find the gradient of your constraints, which in the linear case are simple. It's either 1 or -1 for the positivity and capacity, as we saw before. And you collect all the gradients of the active constraints into the W. And then you go to the next step and you start solving the quadratic problems we had before. So find the reaction force, find the minimal reaction force, which means find the velocity which minimizes this absolute difference, such that this constraint at the velocity level is satisfied. So you need to find the V such that you always have that the gradient of the constraint times your velocity is always greater than this alpha. So again, setting the alpha is basically saying how strict do you want to be with the how open is the feasible velocity set, so the yellow wedge, times the constraint itself, which again guarantees you an exponential decay of the constraint violation. Once you found the V which satisfies these constraints, you then apply the update rule. And how do you know whether you've converged? Well, you need to start getting to a point in the cost curve such that it's plateauing. So the next step of the value of the value of the cost at the next step cannot be much larger than the previous cost. This is pretty standard. And all the constraints are satisfied. If the constraints are not satisfied, you have to keep going. You have to keep iterating. So you go back, you find the new connectivities, you find new pressures, right inside constraints, and you keep going. At the end, at convergence, you return the optimal cost and the optimal fluxes. These might have been, 20 minutes. Somewhat confusing, but I hope it will become clear once we start looking at plots.
If you have an active constraint, that just means you're at the boundary, right? Doesn't mean that your constraint is not followed, right?
Well, it depends if you have greater than 0 or greater or equal than 0.
Okay, right.
It's we usually deal with greater or equal. In fact, we always also have values of up to like 10 to the minus 6 not matter. Like we say, are you satisfying the constraint up to the small epsilon? Because it helps the algorithm converge much faster. Okay, so this is the capacity together with the positivity constraints. So all this is in 2 dimensions, very easy to follow. You have 2 connectivities, so you basically have 2 nodes. No, not even. You have 3 nodes and 2 edges. And your connectivities have to be positive, but they have to lie within a certain capacity. In this case, the capacity is different for each edge. So what you basically have is a rectangle as a physical set. And this could be your global minimizer. So it could be then in the unconstrained case, this is the optimal solution. And it's always outside of the physical set. So your trajectory is going to be trying to get as close to this as possible, maybe going like this, or maybe like this, and then out, and then in again. It probably ends up somewhere around here, depending on the level curves of the cost function. In practice, what this means is when you run the unconstrained case, you get to a lower cost, which is 10.9 in this case. But when you run the capacity constrained algorithm, you end up on a bigger cost. So the 2 points are not the same. You do not end up on the same minimizers. So this one has to be within the feasible set that we saw above in the rectangle, but it's gonna travel for the most part outside of it. So the capacity violation means how many edges are not satisfying the capacity, and a lot of them are not. Like if you start iterating with a very similar algorithm to the unconstrained, it's going to be looking for that point which was outside of C. But it knows that it has to satisfy the constraints because it was built into the algorithm. So it's going to reduce the cost and at the same time fight for, it's going to be two competing forces, reducing the cost and not violating the constraint. And these two things like start competing more closely around here. So this is, for example, you're not violating any constraint, yes, but the cost is still decreasing. So keep going. Maybe you go outside again, cost is still decreasing until it reaches the point where the cost satisfies the condition of the threshold and the violations disappear. Similar, if you have a budget, if you have some constraints, some of connectivities have to be B or less, then okay, equal to B, to be fair, is just this line, but less than B is the shade area. And again, your optimal solution is outside of the feasible set. So what you're going to be doing is probably traveling here until you get to the point on the boundary of the feasible set, which is the closest to the mu star. And this is what we see as well.
Well, that depends on your cost function, right?
Yeah,
You might end up entirely not optimizing.
Yeah, exactly. Depends on the level lines
What's
of
that?
your cost. If they look like this, then yes, it's perpendicular. But if it looks like this, it could be entirely X somewhere else. But for example, we see if you look, sorry, just to address this point, in this case, for example, a lot of the connectivities saturate exactly the bound of the capacity. So they would be on the edge, not somewhere else entirely. Like they would probably come, it would be a point which is directly below the global minimizer, which is just outside.
There's a local minimum that is really inside the physical set. You might not there.
It could be. We don't seem to find that. For instance, in budget as well, it always saturates the bound. Like when we set a budget, it doesn't go for an even lower budget, but it goes for the least budget that we give it. But in theory, it could be possible. I don't know why it doesn't. I think it's case. Yeah, so the budget is the same. Budget decreases, cost decreases. At some point, you have the stabilization of the cost curve and no violation of constraints. And then in the end, you can also put them together. You can have the capacity and the budget, and what's the intersection is when you impose both constraints at the same time. And this will do something very similar. It will reduce the capacity violations, reduce the budget violation up to the lowest point. Finally, we can also visualize this graphically. And in terms of beta, the beta that Katerina was mentioning before, between 0 and 2. In the cost curves plot, it's always 0.5. In this case, it's 1.5 because it gives a better visualization of the routing. So in the unconstrained case, you have few big highways, but obviously their value of the connectivities are going to be larger than what the capacity allows you for. And so what you then end up in terms of network is a network which is much more widespread. Traffic is widespread throughout the network. It's not concentrated on a few edges, because then you cannot have like very congested edges. You can only have a lot of not very congested. So it's like instead of having a lot of highways, you have a lot of B roads, a lot of local roads. And you can see that in the average connectivities. In this case, it's pretty high. In this case, it's low, such that the constraints are not violated. For budget, it's the same. Well, it's not the same as in the average mu decreases, but in a very different way. We see more edges. For instance, this edge, and these ones around it get thicker compared to the unconstrained one. But since at the same time, budget basically means it's very costly to build more edges, we're not going to go for a capacity strategy where we have a lot of edges with little traffic. We're still going to have as few edges as possible, but to have a lot of traffic on very few edges is also very expensive. So it tries to, there are these two competing effects which lead to a few more edges than unconstrained, but not as many as capacity. When you impose both constraints, obviously capacity is still there, so it's going to have a lot of edges. But the average of the connectivity is more similar to the budget, because you still have to satisfy that the sum is below a certain threshold. With that, I would like to thank you. The summary, just going to put it here, and we can go straight to the questions, but I think I'm way over time.